Good morning, one and all. And this is Dr. Diana here. We've been looking into computer organization, and we started with what are the different types of architectures and how architecture is different from computer organization. We have seen that in computer organization, it deals with the design of the exact hardware based on the basic design. So the basic design is given by the computer architecture, and the in-depth circuit design is done in computer organization. So we have seen a basic design of our earlier architectures, and we have seen there are two different types of architectures. One is called as the von Neumann architecture, and the other one is called as the Harvard architecture. In the von Neumann architecture, we see that the instruction and operands are placed and the data are placed in the same memory. So the same memory is used for storing both instruction and data. And once everything is stored inside the memory, you can read them into certain specific memory locations called as registers, which are hardwired to the CPU. So this is what we have seen. And we also saw another different type of architecture called as the Harvard architecture. This Harvard architecture has the same control unit, IO devices, and ALU, but the memory is divided into two. One is used exclusively for storing data, and the other one is used exclusively for storing instructions. So this type of architecture is called as Harvard architecture. None of the desktop PCs or the laptops that we use they use the Harvard architecture. And Harvard architecture is used specifically for certain special purpose computers such as mainframes or in uh, biomedical devices. All of them have a different architecture. They store data and instructions separately. So only under such circumstances the Harvard architecture is used. The basic PC, the laptops, the server machines also run under the same von Neumann architecture. So the von Neumann architecture, we see that the memory is divided for instruction and data. The same memory is used for storing both. And we have seen that any instruction that is read from the memory is of 16 bits wide, and any data that is read is also 16 bits wide, because each memory location is 16 bits wide. So this is what we have seen earlier. And we have seen we need 12 bits for addressing each of these memory locations. Imagine I have 4096 memory locations for the von Neumann basic architecture computer. So we have got 4096 memory locations to be addressed. For addressing each of the memory location or each row in that memory, you need 12 bits. So these 12 bits are used as address for every memory location. Anything you read from memory is going to have 16 bits, or I can say it is 0 to 15. So it's 0 to 15 you have for every memory location, and you have 0 to 4095 such memory locations. That's the memory. Depending on the memory only, all our registers are going to be designed. So every data register will have 16 bits, and every address register is going to have 12 bits. This is the first design rule that we have identified after seeing our memory configuration. So with that memory configuration, I imagine this is my memory, which has got 4096 words or 4096 rows, and each row can store 16 bits of data. I have instructions. All the instructions are stored in the memory. Now, how does a basic computer execute a program? We should understand that. Only then we can design a circuit for executing that program. Okay. So in my memory, I've got some instructions. A set of instructions is called a program. The entire program is stored in memory. Every time I give a program to be stored in memory, it stores in consecutive memory locations. So imagine this is my memory. The first row has got my first instruction. The first instruction is read some value A. So read A is my first instruction. This instruction will be stored in the first row or the 0th memory location. Okay, now the second instruction in my program is read B. Read B will be stored in the next row. Right? The next row is the first row of the or the second row of the memory location. And then I have add A and B. Okay, that is my third instruction. It will be placed in the very next row. So every time a program is given to a computer, in the memory, it is stored in consecutive memory locations. Okay, so if I tell where I have placed my program, I need to specify the first address or the first location or the address of the first instruction. When I mention the address of the first instruction, from there onwards, the computer can say, okay, the next instruction is in the next memory location and next and next. So it starts reading consecutively. So I have to first tell the computer, after placing the program inside the memory, I need to tell from which address the program begins. Clear? Once the computer starts executing, it has to keep track of which instruction it should execute next. Imagine my first row has got read A. My second row has got read B. Okay. This has got read A. And this has got read B. Understand? So I have a computer which is able to read some numbers. So I've got read A in the 0th memory location, and I have read B in the first memory location. Then I have add A and B. This I have in the second memory location. Okay, so this is my program, and for executing this program I need the computer. So once I tell the computer or the CPU where my first instruction starts, that is at memory location 0, it will automatically keep track of the next instruction to be executed. So the next instruction to be executed is read B, and the address in which it can find the next instruction is 1. This 1 is going to be stored in a register, and that register is called as the program counter. Okay, and when I have started executing this instruction read B, it will then, the next instruction to be executed becomes add A comma B, and the address of the next instruction becomes 2. So when I am executing read A, my program counter value will be 1, and when I am executing read B, my program counter value will be 2. All these are addresses, and these addresses, as we have already seen, we need 12 bits for storing an address, which is why the program counter has got 0 to 11 or 12 bits. Are we understandable till here? So, in the program counter is responsible for storing the address of the instruction to be executed next. Because it is storing an address value, trying to address this 4096 words, it is going to be of 12-bit length, or it is going to have 0 to 11 bits. The program counter stores the address of the next instruction. Is that clear? Now I need, once I understand that the some instruction has to be executed, I should bring that instruction from memory into the ALU or the CPU so that I can start executing it. So when I read that instruction from memory, it is read into a register called as the instruction register or the IR. Because I am reading some content from this particular memory location, this is going to represent my entire row. The entire row has 16 bits. So all the 16 bits are read into the instruction register. Clear? And this register is therefore of length 16 bits. So I have written 0 to 15 on top. This is the instruction register. The instruction, once I understand the instruction, the next thing is I need to find out what is my first instruction say? Read A. So this read is the operation. A is called as the operand. Operand is the data upon which I need to perform the instruction. So I have read this entire instruction read A into the register in IR. The next thing is I have to read the data. So once I read the data, I can either place the data in memory or I can read it from an input device. For now, you assume that I am reading from the memory. So when I am trying to read that data from the memory, it is read into a register called as the DR or the data register. This data register is of length 16 bits because any data that I read from memory is going to be of 16 bits. Are we clear till here? So the program counter PC holds the address of the next instruction to be executed. And always remember, all data registers will be of 16 bits because it is storing the entire row. That entire row from memory is being stored. It can either be a data register or a register that holds instruction. Everything is going to be of 16 bits. And all registers that are used for holding addresses are going to be of 12 bits. With that in mind, you can now understand that we have 0 to 11 bits for the program counter, and you have 16 bits for both the instruction register and the data register. Okay, now I have brought the data also. Okay, now once I have brought the data, I can directly bring the data from a register, or in other words, I have to specify the memory location where I have placed data. Imagine this is my instruction, it is somewhere there, and I place the data A in some other memory location, which is, imagine at a memory location 2056. I place the value A, and I place the value B somewhere in another memory location, which is 3573. This is my another memory location. So I have placed instructions at memory location 0, 1 and 2. It will always be in consecutive memory location. My data can be placed anywhere. I have an address for each of my data or the operands. The first operand is in 2056 address. The second operand is in 3573 address. Okay, now in my register PC, the first instruction that I am currently executing is read A. So my PC value is going to be 1 because PC has to indicate the next instruction that I have to execute. So the value 1 is stored in PC. And the instruction register, it stores the instruction that is to be currently executed. So whatever instruction I have here, which is the current instruction to be executed, read A, is placed in the instruction register. Clear? and the data that I want to perform this instruction on is A. I have to read this value A from a particular memory location, right? Now, if you have seen the basic instruction format, which you remember, I don't know if you remember, this is the instruction format we have seen earlier. I said we will see why we are going to use this format. I said the operation code or the op code has 4 bits and the address for that operand is specified using 12 bits. The same way, in this instruction register also, we are going to have first 4 bits indicating the operation read, and the next 12 bits are going to tell me the address from where I have to read that A. Clear? So the address in this example is 2056. So this 2056 is the location from which I have to read that particular value A. To store that address, I am going to use something called as an address register. So an address register is used to hold the address of the data to be used. Is that clear? So that 2056 is going to be placed, this 2056, which is the address of my operand, is going to be placed in my address register, and it is of 12 bits length because it's an address. Now after the computer reads the address register, it goes into the memory, it finds out. Now it goes to that particular memory location and it finds out the value of A. Imagine the value of A that I have given is 8 and the value of B that I have given is 45. Okay. Now this 8 is the data upon which I have to do some operation according to my program. So this 8 is read from memory and it is placed inside the data register. Are we clear till here? So the program counter holds the address of the next instruction. The instruction register holds the currently executing instruction, and the the address of the data for use in that particular instruction is stored in the address register, which is 12 bits or length. And from the address register, using the address register, whatever data you read from memory is put inside the data register, which is of 16-bit length. And I have brought the data here. The next instruction, what is my next instruction here? My next instruction is to read B. Now I have to read another data value, but when I use that instruction, what happens? The next instruction, so the PC, once it has executed, read that data, read A, when it has completed execution of read A, it will start, the computer will see what is the value of PC. So once I complete read A, the value of PC is now 1. So it means that the next instruction that I should execute is at memory location 1. So it is going to start executing the next memory or the next instruction from the memory location 1. So when that has to be done, the program counter has the value 1 till now. So it will read the second instruction, read B, it will put it inside the instruction register, and PC's value will get incremented automatically by 1. So what happens? Once I complete execution of the first instruction, read A, the PC value is going to be incremented by 1. The current value of PC was 1. Once I complete execution of read A, the next instruction is read B. So it is reading from the memory location 1. It is storing this read B inside the instruction register and incrementing the value of PC to 2. Clear? So read B is read inside the instruction register. PC value is automatically incremented to 2, or to indicate that the next instruction to be executed is at memory location 2. So I have brought read B to the instruction register. Okay, now once I have read this, it starts executing this instruction. What is my instruction? My instruction is read B. Just like how I have to mention my instruction format will have read. The first 4 bits will represent read. The second part, or the next 12 bits, will represent the address of B, because my instruction is now read B. So read B should have the address 3573 is the address. This 3573 address is then put inside the address register AR. This address register AR is now going to have the value 3573, which is the address of the data for the current instruction. Once I read that data, my data register is already having the data from the previous instruction. I need to use some other location for temporarily storing this particular value that I have read as B. So I have another register called as the accumulator. This accumulator is the scribbling pad of my computer. Anything that I want to do temporarily, it will be put inside the accumulator. Now B value is put inside the accumulator. Once the accumulator is ready, I have to so I have completed execution of the first 2 instructions, read A and read B. Now what is my next instruction? My next instruction says add A and B. When I try to add A and B, one of my data is in data register, the other one is in the accumulator. So any operation that the basic computer does, it usually stores the result back inside the accumulator unless it is explicitly specified. Unless I tell the computer where to store the data, it will always store the result in the accumulator. So what happens when I complete instruction read B? Once I complete execution of instruction read B, my PC has to be in, next instruction is read, which is add A comma B comes inside the instruction register, and PC is incremented by 1. Okay, with that it stops. And then my address register is not updated because add A comma B, I have given 2 register names. It will not read from the address, and my data values are there in data register and the accumulator. It will add both these values and store the result back inside the accumulator. If for some reason you need some extra storage space, the basic computer also has a temporary register which can store 16 bits of data. Okay. Apart from this, there are 2 registers which can read input and output from external devices. Each of them are going to be 8 bits wide. We will see why they are 8 bits and how we can operate on those 8 bits. And we will see in the later session. For now, you understand that these are the basic set of registers which we are going to have for our basic computer organization. This is the set of registers that we are going to operate on. So let me try listing these registers. You are going to tell me what those registers mean and how many bits they are going to be. So these are the registers. The first one is the data register, the address register, the accumulator, the instruction register, program counter, temporary register, input register and output register. So do you see those names? Now tell me the function of each of this register. Data register is used for holding a memory operand from memory. Address register is used for holding address of some memory location that you want to access. Accumulator is called the processor register. It holds the results of any operation that is done by the CPU. Then IR is the instruction register. It holds the instruction that is currently under execution. PC is the program counter. It holds the address of the instruction to be executed next. TR is the temporary register. It holds some temporary data when required. Input register, it holds an input character which is of 8 bits, and output register holds the output character of 8 bits. Now tell me the number of bits required for each of these registers. Now we should look into our basic principle. All the data and instruction registers will be of 16-bit length, and all the address registers will be of 12-bit length. Having that in mind, what are the data registers we have? DR is a data register, AC is a data register, IR is an instruction register, TR is a data register. So all these registers are going to be of 16-bit length. The data register, accumulator, instruction register and the temporary register are going to be of 16-bit length. And what are the registers that are holding addresses? Addresses will be 12-bit length. So the registers AR, the address register and the program counter are the only two registers that hold addresses. These registers will have a 12-bit length, and special purpose of this input and output registers will have 8 bits each. So these are the registers used in the basic computer. Now once we have understood what these registers are, we are going to look more into the different types of instructions. I said now we are reading some instruction, we are trying to execute. We need to design the hardware for executing those instructions also. So we will see what are the different types of instructions that the computer can execute and how the structure of these instructions is going to change. Okay. There are three different types of instructions. The first one is a memory reference instruction. The second one is a register reference instruction. The third one is an input-output instruction. The instruction format is going to change depending on the type of instruction. And the way we execute that instruction is also going to change based on the type of instruction. So once I have completed this hardware design, I should also design the hardware required for executing these three types of instructions. So we will look into how the ALU is designed and how the control unit can interact with the ALU for performing these operations. For now, I'll just sum up whatever we have learnt in the past two sessions and close this session here. In the first session, we have seen what a computer architecture is. The computer architecture is the basic design of a computer or the behavioral model of a computer. The computer organization means the design of hardware or the components or the circuit that implement the architecture. And we have seen two different types of architectures. The one is called von Neumann architecture, where the same memory is used for storing both instruction and data, and we have the arithmetic and logic unit along with the control unit, which constitutes the CPU. Then you have the random access memory in which both the data and instructions are stored, and then you have an input-output processor through which the input-output devices interact with the CPU. And in the Harvard architecture, the only difference we have is that the memory that is used for storing data is different from the memory that we use for storing instructions. And we also saw that the basic PC, laptop, servers, all that use only the von Neumann architecture. Only special purpose computers such as mainframes and biomedical systems, those use Harvard architecture. Nowhere else Harvard architecture is used. And all our curriculum is going to be based on only the Harvard architecture. And we have seen in the von Neumann architecture, in the basic computer that our curriculum deals with, we are going to look into a memory of 4096 words or 4096 memory locations, each location capable of storing 16 bits. These 16 bits can either be an instruction or data. And when you read that instruction, it will be of the format given here. So you have 4 bits for specifying the operation code and 12 bits for specifying the address. Then you have the data which is stored using all the 16 bits. And in our memory we have seen that once we try to identify that each of these memory locations are accessed using an address, we saw that addressing of the 4096 words or locations will require minimum 12 bits of binary values to uniquely identify each location. So we saw that all the data registers or instruction registers will be 16 bits and all our address registers will be of 12-bit length. We have also seen what are the different types or what are the different registers we can have in the basic computer which access that memory of 4096 words. So we saw that the program counter is used for holding the address of the instruction to be executed next. The instruction register holds the instruction that is being executed, and the address register holds the address of the operand to be used for that particular instruction, and any data that is read from the memory is read into the data register. And accumulator AC is the scribbling pad of the computer. If any temporary data that you have or any result that you get out of doing an operation is stored in the accumulator. Apart from this, you also have an additional temporary register which is 16 bits wide, and you have two different registers for accessing the input and output, which is which are of 8-bit lengths. So you have 8 different registers in the basic computers. 4 are of 16-bit length, 2 of 12-bit length, and 2 of 8-bit length. With this, I will stop for this session. We will look into the different types of instructions in the next session. This is Dr. Diana signing off. Thank you all of you. Stay home, stay safe. Looking forward to seeing you all soon. Thank you.